problem types. Okay. So did we discuss the problem types?
Just started to explain, ma'am.
Okay, fine. So we'll Aditya, please remind me to take attendance later.
Okay.
Okay. So we discussed the different types of problems. We started discussing the different types of problems. These were the various categorizations, deterministic or observable, that is called a single state problem. Okay, so the environment is fully under your control. Vacuum example I gave you, vacuum cleaner with a sensor. So yeah, the deterministic environments ignore the uncertainty. Then we looked into what is called a non-observable multi-state problem. Okay, so in which case you may reach the solution or you may not reach the solution. Okay, so in case it is a vacuum cleaner, okay, here we assume that there's no sensor, so it will have to suck the dirt, irrespective of whether it is moving towards the left or right. Okay, so that's where we call it as a non-observable problem. Okay, so then we have what is called a partially observable problem. So the effect of the action is not clear. For example, driving at the night. So you can see only for a particular distance. You cannot see beyond that. Okay, so the same vacuum cleaner, if we take, we assume that the sensor is attached to it. So then it will suck if there is dirt. Okay, so yeah, so these are the different types of problems. Okay, so some pictures are being given here. You can see here, fully observable. Fully observable is a self-driving car. So where the environment is under your control. Then partially observable, night driving, or this is unobservable, a picture being, okay, this is not that very clear. Okay, so coming to a single agent or a multi-agent problem. Single agent solving a crossword puzzle, multi-agent playing a game of chess with a computer or with an intelligent agent, a human being playing a chess with a computer agent or intelligent agent. Then it can also be categorized as competitive and cooperative. So competitive example is playing chess, whereas driving on a hilly terrain, driving on a hilly terrain could be a cooperative situation, okay, wherein you need to cooperate with the others in the lane to avoid the accidents. Okay, so then if it is static and discrete, static and discrete in the sense one step at a time, the crossword puzzle could be an example. If it is dynamic and continuous, maybe driving the taxi. Okay, so these are the different types of problems. Okay, so most of the real world AI environments, okay, so they are not basically deterministic in nature, but then you may come across problems which fall into one of these category. Okay, so understanding the AI environment is one of the most challenging steps as far as any AI problem is concerned. Okay, then of course we have one more category called unknown state space problem, which is typically the exploration problem. We don't know what the impact of the actions could be. We don't even know what the state is. Okay, so for example, online searching, searching in the internet, you act without complete knowledge of the next state, or even scheduling without a map. So these are all examples of unknown state space problems. Okay, right. So next we move on to another important topic. This is very important from the examination point of view. You can expect it. The problem characteristics. 7 characteristics of the problem. Okay, so we'll take up one by one. Maybe you can note it down. Hope all of you are noting down certain things in your notebook, at least the headings. Are you doing it?
Yes, ma'am.
Okay, Balaram, are you doing it?
Yes, ma'am.
Okay, right. So let's start. These are the 7 characteristics. So let's start with the first problem characteristic. Is the problem decomposable? Okay, so is the problem decomposable? Okay, so in case you are able to split your problems, split your problem into sub problems, let's say 2 sub problems, whatever. Okay, then we can say it is decomposable. Okay, so an example that is being taken to show that the problem is decomposable is what is called a block world problem. Okay, so you will be dealing with this problem in many chapters in various aspects. Block world problem. So here you can see this is the starting state. Starting state. This is the goal state. So goal state is, you want to have B on top of C and A on top of B. Okay, so this should be the final arrangement. And this is the robo hand, which will pick one block at a time, and then it will either drop it down on the table. This can be considered as a table, or it will keep on top of another block. Okay, then it will be able to handle only one block at a time. So what are all the sequence of steps which are being taken to move from the initial state to the goal state? Okay, so that's what should be looked into. Okay, so if you see the starting state, okay, so I told you in the last class also, any problem will have a initial state or a starting state, and it will also have a goal state. Okay, so what are all the steps that you take in transforming the starting state into your goal state or to reach your goal state? So that is, it could be basically be formulated as a search strategy. Okay, so you may have to search for the various strategies to transform your initial state into your goal state. Okay, so that's why we call it as a search strategy or a search technique. AI problem solving using search strategies or search techniques. Okay, so out here, if you see your start state, you can see, see, B is on the table. B is on the table. A is also on the table. Then on C, comma A. Okay, that is C is on top of A. Then hand empty, that is robo hand is empty. Okay, then clear C. There is nothing on top of C. So we say clear C and clear B. Okay, so don't worry about the representation right now. It's a strips representation about which you'll be learning in the, I think, third or the fourth unit. Okay, so it will be having a set of rules, preconditions, along with some addition and the deletion list. So why I took this problem as an example is just to show that a problem is decomposable. It can be decomposed into a number of parts. Whereas your goal state is nothing but you need to keep C on the table, B is on top of C, and A is on top of B. Then the robo hand is empty and clear A. There is nothing on top of A. Okay, so this can be accomplished in number of steps, or we can decompose the problem and reach the goal state in a number of steps. Okay, so that's the first one. Is the problem decomposable? Then second one, this is another problem which we'll be taking up at a later point of time, another toy problem. It is also called the 8 puzzle problem or the sliding block problem. It is called the sliding block problem. Okay, so this is the start state and this is the goal state which you want to accomplish. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you would have played this as kids, or maybe even now, maybe you, during your free time or something, you would have come across this and you would have already, solved this sort of a thing, 8 puzzle problem, a sliding block problem. Okay, so what we are looking into is the second characteristic of the problem. Can the solution steps be ignored or undone? Okay, so suppose we have a let's say a mathematical theorem. Okay, so we proceed by first proving a certain lemma, thinking that it's useful, but then after some time we understand that it's not useful at all. Okay, so whether we are in trouble, it's all the effort, it can always be undone. Okay, so proving a mathematical theorem, you can always undo it. Though it is wrong, you can come back, you can backtrack, and you can ignore it, and it can be undone. Okay, it's only a waste of effort. Same way, the 8 puzzle problem, what is being given here, depicted here, or the sliding block problem. Okay, so in the process of from the starting state, in the process of moving towards your goal state, you would have performed many incorrect steps. You would have performed many incorrect steps. Okay, so we can always backtrack it and then it can be undone. Okay, so only thing is that you will have to perform an additional step to undo each of your incorrect step. Okay, so these are the case of these two things. But then now consider another example. Let's take the case of problem of playing the chess game, a game of chess. Okay, suppose suppose the chess player program is making a stupid move, and it realizes that it's made a stupid move only a couple of moves later. Can you undo it? Can you undo it? I simply
ma'am.
can, yeah, I cannot do that. I cannot do that. Okay. So I'll have to, I mean, that is a case where it cannot be undone. Okay. So either you will have to, I mean, accept the defeat or whatever, or proceed with the current strategy, or, I mean, you will have to start the game all over again. Okay. So these are the three different types of problem what I just gave you. Okay, these are another problem characteristic which should be taken into consideration. Can a solution step be ignored or undone? If it is a mathematical theorem which has to be proved, definitely some amount of effort has gone into doing it, but then it can always be undone. Same case with an 8 puzzle problem, but then when it comes to a game of chess, it's a matter of winning or losing. So you cannot undo it. That's the second thing which has to be taken into consideration. Then, yeah. So with this, we have we can categorize the problems as three. One is ignorable, ignorable, as I just mentioned, proving a theorem or a lemma, okay, or recoverable. Okay, so 8 puzzle, I make some stupid moves, I can always undo it with some additional steps, and I can recover from the mistake and then again proceed. Only thing is that the number of steps may be more. It may not be the optimal solution for going from the goal initial state to the goal state. Whereas if it is an irrecoverable problem, then I cannot undo it. So we have three categories. So please make a note in the your notebooks: ignorable problem, recoverable problem, and irrecoverable problem. Okay, right. So now coming to the next characteristic. Next characteristic is the universe predictable? Is the universe predictable? Okay, yeah. So now again, when we take your sliding block problem or your 8 puzzle problem, okay, so every time we make a move, that is, you slide the block from one location to another location, we know exactly what will happen. So that means you will be able to, it is possible to plan the entire sequence of moves. And then you can be confident that we know that what the resulting state will be. Okay, so then even we can plan to avoid the stupid moves, or we can even plan that we are not undoing any proper moves. Okay, so all these things, so the entire, I mean, we are able to plan everything here in the case of a 8 puzzle problem. Okay, so the complete a control structure that will allow backtracking will be necessary. Okay, but then that may not be the case in many other problems. Okay, so for example, if you are playing a game of bridge, I hope you would have come across this bridge game, a card game. Card game. So the type of planning, what I just mentioned in your 8 puzzle problem, okay, that planning process may not be possible in a bridge game, a card game. Okay, so like one of the decisions we will have to make is which card to play on the first trick. Okay, so what we would like to do this is to plan the entire thing, before making the first play. But now it is not possible to do such a planning with certainty, because we don't know, we cannot exactly know where all the cards are or what the other players will do when their turn comes. All these things we don't know. So the best thing we can do is to investigate the various plans, and then to find out the probability of the various outcomes, and then choose a plan which has the highest estimated probability of leading to a good score or whatever. Okay, so it all varies from problem to problem, whether it is a 8 puzzle problem or a bridge game. Okay, so there is always a difference. So that is what it addresses the problem: is the universe predictable? Okay, is the universe predictable? So in case of uncertain outcomes, just like our bridge game, we follow the process of planned revision as the plan is being carried out, and the necessary feedback will be provided. Okay, so in this case the planning is not that very easy and it could be expensive. Okay, that's a third one. Are you all listening?
Yes, ma'am.
Dilip, listening? Dilip, Deepak.
Yes, ma'am.
Okay. Deepak is listening. Okay. So, and coming to the fourth, okay, Deepak. So, is the fourth characteristic. Please make a note of all this. Very important from the examination point of view. So, yeah. The next is, is a solution an absolute solution or a relative solution? Okay. For example, if it is Mark, you will come across this what is called predicate logic, a formal language representation where you can represent the facts. Okay. So, for example, if the marks is 92, then you get grade. The grade is O. So that is, you have an absolute solution for it. Whereas if it is in the case of a traveling salesman problem, TSP stands for traveling salesman problem. All of you would have come across that problem somewhere in your data structures or DAA. Okay, so what you do in that case, traveling salesman problem, what do you do? Manikanta, what do you do in traveling salesman problem? Traveling salesman problem. Can somebody tell what is being done in one line? That's it. What is the objective of a traveling salesman problem?
Maximum distance in minimum possible time.
Yes. Starting from the, starting city to the end. You explore all possible solutions and which is the shortest path. That's what you do it. Okay. So it's basically it's a relative solution. That's when we call it as a relative solution. You explore all possible solution. Okay. So whether it is an absolute solution or a relative solution. Okay. So next is then, is the solution a state or a path? The next characteristic is whether it is a state or a path. Okay. The thing is, when you tell a sentence, okay, so it may have different interpretations. It may have different interpretations. For example, I'm telling the bank president ate the dish of pasta salad with the fork. So when I say, okay, let me add the word bank here. The bank president ate the food or pasta salad with a fork. So when I say bank, what can you infer? Okay, when I say bank, so it can either mean it can either refer to a financial institution or to the side of a river. Okay, so only these may have a president, whatever. Okay, so again the food, all these things will have different interpretations from different people. Okay, so that's where your natural language processing and other things come into picture. Okay, so the record of processing by how the interpretation was arrived is we generally don't look into it. Okay, to solve a problem of finding the interpretation, we need to produce only the interpretation. Okay, how we reach that interpretation, we generally don't tell it. Okay, so in contrast, if we must produce such an interpretation, the final state along with the path that we found to the state along with the sequence of operations to produce the final state. Okay, so that could be, it may not be that very easy. Okay, for example, if it is a water jug problem, about which you will be learning very soon, a toy problem, water jug problem. So in this case, how you reach the solution will be important. Okay, so in which case, that's what it means. Okay, the final state along with the path that we found to the state. Okay, so it varies from problem to problem. Okay, if it is a water jug problem, it is not sufficient that to tell that we have solved the problem and reach the final state. So in this case, we must report how we reach the final state and how we tread through the various paths and reach the final state. Okay, so these two examples, your NLP, natural language processing, interpretation, and water jug problem. So that basically illustrates the difference between the solution, whether the solution is a state or the solution is a path. Okay, so we'll be taking up all these problems very soon. Okay, then if it is a traveling salesman problem, as I just mentioned, the traveling salesman problem, so that is an example of a path, because we are interested in knowing the path that the salesman takes. Okay, so he wants the route to be as short as possible. Okay, so the goal state is not specified in advance. Moreover, our objective is it has to be as short as possible. Okay, so the final state may be given, but then the important property is one of the whole path. Okay, so that is basically a path. Okay, path, but the difference between a path and a state. Okay, then you have other examples. Examples for state could be your crossword puzzle, what state it is, or your 8 queens problem, or your n queens problem, or your magic square, natural language understanding problems, or your mathematical theorem proving. Okay, so the objective out here is whether you complete or not. Okay, the main interest is the crossword is completed. How it is completed, no one worries about it. Whether you have solved the puzzle or not, people are interested in knowing, but then how you solved it, many cases, in the case of a crossword puzzle, they may not be interested in knowing. Okay, so even in the natural language processing example, because of the interaction between the various components, some search may be required to find a complete interpretation. Otherwise, we are concerned only about the solution. Okay, so that is, it varies from problem to problem, whether the solution is a state or a path. Okay, then the next one is the role of knowledge. The role of knowledge. Okay, so what about the role of knowledge? So let's, okay. For example, yeah, is lots of knowledge required to solve a problem, or is knowledge only to constrain solutions? So that's a question. So for example, if it is in the game of playing a chess, okay, so we have a very efficient computer. Let's say we have a workstation or we have a supercomputer, okay, and all the rules for determining the legal moves are known, and it's being fed into the knowledge base, and you have a very efficient control strategies also available, then definitely the problem can be solved after the application of certain tactical moves. Okay, so the computer will be able to solve the problem. Okay, so now the same, I mean, all the same facilities are being given, the same workstation or a supercomputer with all the computing infrastructure and other things are given, then whether it can easily give an answer to a question like which party will win in the election. Which party will win the election? Okay, so but then for that, whatever is being fed into the knowledge base may not be sufficient to give a answer, a accurate answer to such a question. Okay, so you may have to scan the newspapers to find out which party supports which which candidate, and I mean, so many things. What are the good things they did? How are the taxes being lowered? What policies they have adopted? A lot of knowledge has to be knowledge is required in this sort of a problem. So both cannot be compared. So knowledge also plays a important role. Okay, so yeah, that's the sixth question. I mean, sixth characteristic. What is the role of knowledge? Okay, so to answer a question like which party will run the win the election, you need to get a lot of information by scanning the websites or newspapers. So knowledge is required. Okay, so the computer, however intelligent and powerful it is, it will not be able to combine all these aspects and analyze them, and it will not be possible for it to arrive at a accurate solution. Okay, so that's what I wanted to stress upon. Okay, so what I want to tell you is your system or your computer can give a solution to a problem which have some legal rules associated with it, and maybe depending upon some sentiments or emotions or likes or dislikes. Okay, so but then many cases it will not be able to come up with a accurate answer. Then the next one is, the next characteristic is, does the task require interaction with a person? Okay, does the task require an interaction with a person? Okay, so there are two types of problem. One is solitary, and yeah, the second one is conversational. It varies from problem to problem. Okay, yeah, the solitary means the computer is given a problem description and it produces an answer with no intermediate communication and with no demand for an explanation of the reasoning process. Okay, so no demand for explanation and other things. So then we can call it as a solitary problem. Okay, so conversational problem means there is in between intermediate communication between a person and a computer. Either some additional assistance may be provided, or some additional information may be provided, or whatever. Okay, so yeah, so for a particular application, I mean, one or these type of the categorization could be done. Okay, so these are the, I mean, that's the task. I mean, this is another aspect which has to be looked into consideration, whether it is a solitary problem, okay, or a conversational problem, which requires intermediate communication between a person and the computer, either to provide some additional assistance or to provide some additional information to the user, or both. Okay, so these are the 7 characteristics. These are the 7 characteristics of a problem which under which the solution must take place. So whatever I have told you just now, these are the 7 important characteristics of an AI problem under which the solution must take place. Okay, so next, so we move on to the next topic, problem space and search. Okay, so this is what we have completed right now, problem types and characteristics. So next, moving on to problem space and search. Okay, so already I have mentioned that when you say an AI problem, what are the things it will have? It will have a initial state, then it may have one or more final state or goal state, then it will have a set of rules, operators, or it can also be called actions, which will move the problem from one state to another state. Okay, so together this initial state, the action, goal state and the actions, whatever is required for transition, together what do we call this as? Last class I gave a name for it. Together, all these things together, your initial state, one or more goal states, and a set of rules, together what do we call this as? We call it by a name. Can you look into the Romanian map problem and tell me what the name I gave there? Somebody. All these things together, what do we call it as? Atul, what do we call it as? All of you had made a note of all the problem components, right? It is called the state space. Are you all listening? It's called a state space. Your initial state, your goal state, what are all the rules, operators, actions, whatever is required. Okay, so that is together. I mean, everything is, we call it as a state space. Okay, so that set of all states reachable from the initial state by any sequence of actors, actions, or operators. Okay, so when you say AI technique, so that is something which is being built from a problem solving perspective. This again and again, I have told it a couple of times. Okay, so you will have a initial state and a goal state. Okay, so you don't know the path means you will have to search for it. So for that, you will have to adopt some search strategy or search techniques about which you will be learning in the second unit. Okay, so that's what I just mentioned. You have an initial state and a goal state. If you don't know the path, how to reach from the initial state to the goal state means you will have to search for it. Okay, so the objective of problem solving is basically to find out the set of actions, how you are going to reach the goal. Okay, so that's what. So what are all the actions which are being taken? Okay, for example, I am sitting here. On a chair. I want to switch on the air condition. What should I do? I will have to get up from my place. I'll have to stand. I will have to walk to that location, then switch on the device. Okay, switch on the device. Okay, so from the initial state, that is sitting here, to my goal state, that is the device is being switched on, the AC is being switched on, I need to follow a certain path. Okay, I need to follow a certain path. Okay, so that's what I wanted to tell you. Fine. So now we are being given an example. A toy problem is being given an example to enumerate all the possible states here. The problem which is being taken is the monkey banana problem. Have you heard of this monkey banana problem? Heard of this problem called the monkey banana problem? At least tell yes or no. If you tell yes, I'm not going to ask you what the problem is. I'm going to tell you what it is. Anybody heard about this problem, monkey banana problem? At least tell me no.
No, ma'am.
No. Okay. So now let's see what this problem is. Okay. So, and again, there is another terminology which comes up called abstraction. In the sense, when we are proceeding from the initial state to the final state, we may be following many number of paths and we may come across many states, some of which may be unnecessary, or we can ward it off, or we can eliminate it. So that process is what is called abstraction. Okay, removing the unnecessary states or unnecessary steps, we can call it as an abstraction. Okay, so yeah, so let's see what the monkey banana problem is all about. So by looking at the diagram, can you make out something? This is the monkey banana problem. Monkey banana problem. So a monkey is there in the room. Monkey is there in the room. A bunch of banana is hanging from the ceiling. A bunch of banana is hanging from the ceiling. So the monkey cannot reach the banana directly. Okay. So however, in the room, there is one chair and one stick. Okay. So the monkey can, push this chair, make it directly under the bunch of banana, get onto the chair, and using the stick, it can reach the banana, put it on the ground, or pluck it and eat it. Okay, so our question is, what are all the actions the monkey should take? What are all the actions the monkey should take? So this is our initial state. This is our initial state. This is our goal state. Goal state is monkey standing on the chair and catching the banana with a stick and able to pluck the banana and eat it, or put it on the ground, then get onto the ground, then pick the banana and eat it. Okay, so have you understood the scenario? Okay, so you know how to get the solution. Okay, so in this case, you know what are all the actions the monkey should take. Okay, so now let's look at this problem from a problem solving perspective. I told you what this is. This is an example for a toy problem. Toy problem. Toy problem. Okay, so what are all the actions a monkey should take? Now you are well aware of the scenario. Even you know how the sequence also you know very well. Okay, so monkey is on the ground with empty hands. He's grabbing the stick. Monkey is with the stick, climbing on the chair. He's on the chair with the stick. He waves the stick. Banana falls onto the ground. He's getting off the chair. Monkey is on the ground, dropping the stick, grabbing the banana. Then he's eating the banana. Okay, then some other sequence can also happen. Okay, so yeah. So, but then whatever the final goal is, monkey is going to eat the banana. Okay, so now here in this particular situation, what is the initial state? We are always looking at in AI, we always look at it from a problem solving perspective. From looking at a problem solving perspective, what is the, so we'll have to identify what the initial state is, what the goal state is, what are all the actions. Okay, so what could be the initial state? Initial state is monkey is on the ground with empty hand, and the banana will be suspended from the ceiling. So this is the initial state. The monkey is on the ground with the empty hand and the banana is suspended from the ceiling. Okay, so the goal state is monkey is eating the banana. Okay, so what are all the actions required the monkey should take to eat, to enable it to eat the banana is what we are interested in. Then actions. What are all the actions? Actions are nothing but the operators. All the actions are the operators. Actions are the operators. Okay, so you climb the chair. or get off the chair. Okay, so these are all individual actions. Okay, so the sequence in which you are going to put it is different. Okay, so how you are going to put this action? The climbing the chair will come first, or getting off will come first. How we are going to individually sequence it is a different question. Okay, so then grab X. Maybe X can be banana. Okay, grab X, or okay, even it can be stick. Okay, so eat the banana. Okay, so this is what the action is. So what I just wanted to tell you is, yeah, so I mean, with this toy problem, what the initial state is, what the goal state is, then what are all the actions or actions involved in this particular thing. Okay, so even when you say the sequence, it can be one sequence or it can be multiple sequence. This is one sequence, what I just mentioned. There can be another sequence also. There can be another sequence also, but finally it reaches to this particular goal state. Okay, so one of that particular sequence you will be choosing in order to get the possible result. Okay, so in the shortest time you need to reach your goal state. That is, in the shortest time the monkey should be able to get the banana and eat the banana. Okay, so we told all these things very easily. Okay, but actually the solution procedure for this particular problem, it requires a lot of planning algorithms. Okay, so that's what planning algorithms. Planning algorithms. Then again, there could be a question like whether the monkey is intelligent. Okay, so of course monkeys, even if they are coming to that particular room for the first time, monkeys have the ability to learn new things, that it has to push the chair. It wouldn't have done such a thing before itself, but still it is able to learn some things. So learning, adapting, all these are various aspects of AI. Learning, adapting. It wouldn't have come to this particular room before, but still it knows that it has to push the chair and it has to get onto the chair, and then it is learning new things. Okay, so a monkey, I mean all these aspects has to be taken into consideration. Okay, so it may be, you cannot totally call it as an instinct. It could be a partly learned behavior also. Okay, so I mean, this is the example which is being given to you. So this is actually one of the toy problems which is being given in AI to understand the concepts, the various aspects involved in planning. Okay, so now I hope it's clear. So next, coming to, that's regarding your monkey banana problem. Okay, formal description of the problem, the state space, and how do we go about it. Okay, so what are the components of the problem? Okay, then coming to the problem solving. So we have two types of problems. It could be a general purpose method, or it could be a special purpose method. Okay, so let me tell you about the general purpose method. Okay, so I gave the example. I'm sitting here, I want to switch on the AC. So what do? I just get up from my place, I stand up, then walk to the location, and then switch on the device. Okay, so when I am sitting here, so just listen to the last, read the last line here. I'm trying to tell you what this means end analysis is. Okay, so it's applicable to a wide variety of problems. Yeah, it's a step-by-step or an incremental reduction of the difference between the current state and the goal state. Difference between the current state and the goal state. That is what is called means end analysis, MEA. Okay, so I'm taking that example. I'm sitting here, I want to switch on the AC. Okay, so what I do is I get up from my place, I stand, I walk to the location, then switch on the device. Okay, so when I am sitting in my chair here, okay, so the difference between the current state and the goal state is very huge. But then when I reach that particular location, the difference is reduced. Okay, so what I mean to say is, as I move towards the goal state, the difference is getting reduced. Do you get my point? That's what is called means end analysis. Later we'll take up the algorithm for this. Okay, so that comes in another unit. So that can be considered as a general purpose method. Okay, So means and analysis is this: as I move from the initial state, so the difference is reducing. In this case, it is reducing. In some other case, it could be increasing also, because to switch on the AC, rather than going to the particular switch, if I go to some other staff room, roam here and there, and then come back, definitely the difference will be increasing. Okay, so that's why I'm telling incremental or reduction. Okay, incremental or reduction. Okay, so that's what is a general purpose method. Then we have what is called a special purpose method. Special purpose method means method is very specific. It is not suitable for anything else. Okay, it's a tailor-made solution for a particular, it's tailor-made method for a particular problem. Okay, so that's the two different types. Okay, so your special purpose method and the general purpose method. Okay, then we'll move on to the toy problems. I think I have already told you what a toy problem is and what a real world problem is. Okay, so your toy problem is basically used by the researchers to compare the performance of the various algorithms. Okay, we'll be looking into 7 to 8 toy problems, and you, of course, you will be working out one or two in the lab also, like your monkey banana problem, or the missionaries and the cannibal problem, or the tic-tac-toe, or the vacuum cleaner problem. Whereas your real world problem, what could be an example for a real world problem? Can you tell me an example for a real world problem? Manitarun, real world problem. Can I call this as a real world problem? What is this? Traveling salesman problem, your touring problem. That is a real world problem. Touring problem, or your VLSI layout, or your robot navigation, or your internet searching. These are all real world problem. Okay, so right. So that's the difference between a toy problem and a real world problem. So first we'll look into a toy problem. We'll be looking into toy problems in this particular unit. Real world problems, I think only this unit we don't have it. Okay, so first let's try to understand the first problem, the vacuum cleaner world problem. Okay, so imagine you have a intelligent agent. Our intelligent agent is a robot vacuum cleaner, Are you all listening?
Yes, ma'am.
Yes.
Okay, so let's imagine that our intelligent agent is a robot vacuum cleaner. So as far as our world is concerned, we are considering only two locations, A and B. So the robot can be in either one of these rooms. Okay, so there can be dirt either in 0 room, which means there is no dirt at all, or dirt can be in 1 room, or dirt can be in 2 rooms. Our objective is to clean. Okay, so if you look here, if you look at this segment of code, you can see here, if you have dirt, then suck the dirt. The robotic vacuum cleaner will suck the dirt. Okay, so I just mentioned you have two locations, A or B, or let's say you have two tiles. You can be more clear, specific, telling that it's more two tiles, right tile and the left tile. Okay, so wherein you will have to move to the right or to the left. So here the location of A is left tile. That means if location is equal to A, then you will have to move to the right, because the location of tile A is left. Or if the location is B, then you will have to move to the left. Okay, so that's what. So this is a very simple agent. We can call it as a vacuum agent, a simple vacuum agent. Okay, so now let's try to understand what are the various states in this. Okay, so what are the various, what is the initial state, what is the final state, what is the various states involved in this? Okay, first let's see what the state is. State. How do we get this 8 here? Okay, so the state is basically determined by the agent location and the dirt location. Okay, so the agent is in one of the two locations. Okay, so which one of the two locations means in which there could be dirt or there need not be dirt at all. Okay, so you will have 2 into 2 to the power 2, that is 8 possible world states. Okay, so this is because we are considering only 2 tiles or 2 locations at a time. Okay, in case it is a larger environment, n into 2 to the power n. Okay, so can you tell me what are these 8 possible world states out here? Or can you just draw it in your notebook? Are you able to visualize it and imagine what are those 8 possible world states as far as a vacuum cleaning intelligent agent is concerned? The 8 possible states. In that, one will be, there could be initial state, there could be final state, there could be more than one final state or goal state. Anybody able to visualize it? What are those 8 possible world states? Vishal? Srinjay? What are those 8 possible world states? I'll just show you in the next slide. Before that, are you getting some idea regarding what it is? It is this. These are the 8 possible world states. Okay, so what are these states? What can I call these 2 states as? What can I call these 2 states as?
Initial and final.
This is initial state.
No,
This
it's
is final state.
final state.
Clean means that will be the final state. Clean is final state. So state 7 and state 8 is final state. I hope all of you understand the pictorial representation. This is our robotic intelligent agent vacuum cleaner. This is the dirt. So what about the initial state? Initial state can be any of these. Initial state can be any of these. Even a clean state can be an initial state. Okay, so any of these state can be an initial state, and state 7 and state 8 can be our final state or the goal state. Okay, so these are the,
Ma'am, it's almost the time. Can we take the
Time.
attendance?
Oh my, I have not taken attendance. My God, our syllabus is also not moving and they've not taken the attendance. Right. Fine. Let me quickly take the attendance. Right. So quickly answer your attendance. Shruti,
Present, ma'am.
Ryan. Ryan is not regular to class. Aditya Sharma.
Present, ma'am.
Sudha Ramakrishnan.
Ma'am.
Sanjay Kumar.
Present, ma'am.
Dipanshu Kumar.
Present, ma'am.
Okay. Vishal.
Present, ma'am.
When I ask a question, you don't open your mouth, no, Vishal. Srinjay.
Present, ma'am.
Muhammad Fasil.
Yes, ma'am.
Nitish Venkatesh.
Present, ma'am.
Dilip Kumar.
Yes, ma'am.
Shruti Kaushik.
Yes, ma'am.
Nitin R.
Yes, ma'am.
Venkata Mani Kanta Reddy.
Yes, ma'am.
Ankit Kumar Singh.
Present, ma'am.
Himanshu Kumar Maurya.
Present, ma'am.
Atul.
Present, ma'am.
Niharika.
Present, ma'am.
Indu.
Present, ma'am.
Sai Hemant. Sai Hemant is there?